Okay, so this is the 13th lecture in the series on algebraic number theory, and today I want to talk about the concept of integral closure. So I'm going to start basically with an outline. So let's go ahead and outline what I want to talk about in this lecture. So the first thing is I basically want to give a definition of this concept of integral closure. Oh, that's weird. The line kind of went right through the... Oh, I'm just going to ignore that. So I want to give a definition. And first example, of integrally closed domains. The next thing I want to talk about is, so accompanying with this notion of a domain being integrally closed is the integral closure of a domain. So I want to talk about the integral closure definition. I want to do an example. So the example I have in mind is this symmetric polynomial ring. And the third thing I want to talk about is a proposition on the fraction fields of integral closures. Okay, so it turns out that basically when you take an integral closure in a given field, that field is actually the fraction field of that integral closure. And I'll be more careful about what that means later. So these are the main three topics I want to talk about. Let's go ahead and start with what it means for something to be integrally closed. I'm going to start numbering my propositions just so that I can reference things a little bit easier throughout the videos. So this is going to be 13.1. This is a definition. Okay. So I'm going to let A be an integral domain. With field of fractions K. And we say A is integrally closed if, okay, so how do I tell when a domain is integrally closed? If the only elements of K integral over A, maybe I didn't need a comma there, are those already in A. Okay, so just to start off with an example, the easiest example, I claim Z, the integers, are integrally closed. Okay, how do I prove this? Z has field of fractions Q. I'm going to take an arbitrary element of Q, which is integral over A, and show that it has to be an integer. Let A over B be in Q. b integral over a. Or sorry, yeah, integral over z. And I'm going to show that b necessarily divides a, so that this is actually an integer. Okay, so by definition of integral, I can find some polynomial, some monic polynomial that this satisfies. Let f of x, let's call it x to the n plus c sub n minus 1, x to the n minus 1, and so on, plus c naught. This is a polynomial with integral coefficients. Have a over b as a root. What does this mean? In terms of this equation, it means that a over a to the n over b to the n plus c to the n minus 1 times a to the n minus 1 over b to the n minus 1 plus c naught plus c naught equals 0. If I multiply through by b to the n, I'll find that multiply by b to the n, I'll find that a to the n plus c to the n minus 1 times b times a to the n minus 1 plus b to the n c naught equals 0. If I subtract a to the n over and factor out of b, subtract and a factor, I'll find that a to the n, negative a to the n equals b times some stuff, c to the n minus 1 times a to the n minus 1 plus b to the n minus 1 c naught. Okay. From here I don't quite get that b divides a to the n, or sorry, I don't quite get that b divides a. However, we can assume a over b is in lowest terms, so that a and b are coprime. And then by Euclid's lemma, b necessarily divides a. Thus, this fraction, which is integral over z, is necessarily actually an integer. Okay. So z is, I should label this, sorry. Z is necessarily integrally closed, and I'm not going to prove this, but you can think about it for a little bit. Proposition any u of d is integrally closed. So basically you can replicate this proof for z, but instead of having z, make it a u of d, and it'll be very similar. Okay. Okay. Proof. Exercise. Generalize the above. Okay, so this is the condition of being integrally closed. Not all integral domains are integrally closed. This is where this concept of integral closure comes in. Okay. So maybe there are some elements of your field of fractions which are integral but not actually contained in your domain. It's useful to have a name for those. So definition, this is 13.4. I'm going to let L be a field, so not necessarily the field of fractions, just any field. A field containing an integral domain A, and I'm going to call the ring of elements of L integral over A this is going to be the integral closure of A and L. Okay. In the case, so this is kind of what we talked about at the end of the last lecture. In the case A equals Z and L a finite extension of Q, we call this ring the ring of integers of L the ring of integers of L and denote it O sub L. Okay, so in the for example, this is 13.5. So the simplest example, which we just computed above, I know that the ring of integers of, let's say Q, is just equal to Z. I can do this more generally if, for example, the ring of integers of let me think. Maybe you have like the field of fractions of a UFD. Or no, sorry. I think actually maybe I can't prove right off the bat that rings of integers are what they are just yet. Now this is the simplest possible example. Maybe I can also say the integral closure of, let's say, Z adjoin I. This is a domain, a UFD, and let's say Q adjoin I. The field of fractions is Z adjoin I. Okay. So I know this since Z adjoin I is UFD, and proposition 13.3 tells us that those are integrally closed in their field of fractions. Now the next example is going to take a little bit of work. So I'll call this 13.6. Let's be example. I claim that the integral closure, I guess first I should start off with the preliminaries. Okay. So I'm going to let K be a field. And S sub I will be the ith symmetric polynomial in m variables. Elementary symmetric polynomial. M variables. If you're not sure what this is, I'd see lecture 10. Talk all about symmetric polynomials there. Okay. I claim the integral closure of K join S1 through Sm is, I guess first I have to tell you what the integral closure is in. And let's say K, you join X1 through Xm, this field of rational functions in m variables, is just polynomials in m variables. Okay. So this is our first example of a ring where we actually have to do a bit of work to compute the integral closure. Now, the way we're going to prove this is kind of clever. So, proof. The first thing I'm going to notice is that, so this guy, if I just take the polynomials, this thing is a UFD, and thus integrally closed. So polynomials here, which are integral over K join X1 through Xm, necessarily lie in K join X1 through Xm. Now, any element of this field of rational functions, which are integral over, so if f in here is integral over the symmetric polynomials, well, then it's necessarily integral over the regular polynomials, because symmetric polynomials and the symmetric polynomials are just polynomials in m variables. So we have like a containment here. So this is integral over K join X1 Xm. Thus, since this is UFD and is integrally closed, f necessarily lives in this polynomial ring. So this essentially gives us one containment. It tells me that elements of the integral closure of the symmetric polynomials are regular polynomials. Okay. To get the other direction, so thus k join x1 through xm contains the integral closure of k join s1 to sm. Okay, to get the other direction, so I need containment the other way, that every element here is integral over k join s1 through sm. Since I know that that is a ring, and clearly contains k, it suffices to show, so to get the other containment, it suffices to show that each xi is integral over k join s1 to sm. Now the key here is to essentially cook up a polynomial which has these xi's as root. This is kind of, it's hard to come up with, but easy to verify. So, well, yeah, I guess maybe, for me it'd be hard to come up with, it's maybe more accurate to say. So the observation is basically to consider the following polynomial. Consider t minus x1, t minus x2, and so on, t minus xm. And you'll see, okay, basically if you expand this out, you'll see that the coefficients are exactly the nth symmetric polynomials. This has xi as root. And the coefficients, maybe not exactly, maybe up to sign or something. Coefficients are symmetric polynomials. Yeah, I think not only are these symmetric polynomials, I think they'll be elementary symmetric polynomials, so you don't even have to do any extra thinking. Elementary symmetric polynomials. Okay, so if you really, I guess really you should go through and check, like think about what these coefficients are going to be, but they will be symmetric, elementary symmetric polynomials up to sign. Okay, so why go through this little lengthy example? It shows you a useful technique for computing the integral closure of things. So 13.7, remark. To compute integral closures, find an integrally closed ring in this case we found a UFD containing your interesting ring. Okay. So finally, there's one last topic to cover in this lecture, which is the following proposition will prove. So we finally prove the following. If L is a field containing A, I'm going to get this statement right. So one second. Okay, yeah. If L is a field containing A, an integral domain, and O sub L is the integral closure of A, then L equals the field of fractions of O sub L. Okay. So one immediate corollary of this basically tells you that if L is not the field of fractions, then A is not integrally closed in L. Okay. So the contrapositive is useful, is what I'm saying there. So this is going to follow from the following corollary. This follows as a corollary from the following proposition. Okay, so this is 13.8 proposition. Let K be the field of fractions of an integral domain A and L a field extension of K so essentially you've got A sitting inside K sitting inside L. If there's an adjective here that I'm missing. If L is I think maybe this is as stated, this is not quite true. Really, I need L to be a finite extension of the field of fractions, or at least an algebraic extension. So I'm going to rewrite this carefully. So if okay, I'll just state it for the number field case. It holds more generally, but the case we really care about is the number field case. If L is a number field, i.e. a finite extension of Q, then L equals the field of fractions of O sub L. Okay. Gosh dang it. Having trouble with everything right now. Okay, so we'll just state it like this. It holds more generally, but it's fine. So 13.8 proposition. Okay. So it's gonna follow from this 13.8, let K be a field of fractions of an integral domain A, let L be a field extension of K if alpha in L is integral, or is algebraic over K, then D times alpha is integral over A for some non-zero D in A. Okay. So the proof of this is really not too bad. You take alpha, which is algebraic over K, it takes some polynomial alpha algebraic over K with, let's say, minimal polynomial x to the n plus c n minus 1, x to the n minus 1, and so on. Okay. I can find some common denominator of these CIs. Let D and A be the common denominator. Then I just consider what happens when I multiply this. Then d to the n times alpha is a root of x to the n plus cn minus 1 times d x to the n minus 1 plus d to the n c naught. Okay, if you plug in sorry, this should not be d to the n, this should be d alpha. Not sure why this doesn't work the way that I intend. Why? Okay, well, I'm not going to figure it out right now. Okay, there we go. D alpha is a root of this guy. Okay. So this pretty much finishes the proof of this proposition. This polynomial has integral coefficients, or coefficients in A, by the choice of D as the common denominator of these things. Once I know that algebraic, I can find a D which makes algebraic elements integral when I multiply. And I know that if L is a number field, any element of this number field is algebraic over Q. Therefore, I can find an integer that makes it integral over, I can find an integer which makes it integral over z, which in turn puts it in the field of fractions. Okay. So we see for any alpha in L, there exists a d not equal to 0 in z even, such that d alpha is an O sub L. Thus, L equals the field of fractions of O sub L. Okay, so that pretty much wraps up this lecture. Next time we'll talk about a couple more propositions involving integral elements that end up being useful. In particular, we'll give a useful criterion for checking if an element is integral or not. That's different than the proposition we proved last time. It has to do with minimal polynomials. So